I'm not gonna lie. When I first learned this stuff and the first bunch of times I taught it, I really struggled wrapping my head around this one. I found this one to be a little odd. The topic of the day is something called single slit diffraction. So I can wrap my brain around double slits. If we have two narrow openings, light from the one opening interferes with the light from the other opening. I can wrap my brain around diffraction gratings. Light from one opening interferes with light from the other openings, and it's got the cool effect of stretching out the dark spot. But single slits are just weird. Light is only going to go through one opening, but the light that goes through one part of the opening is going to interfere with the light that goes through another part of the same opening. So how I'm going to draw it is I'm going to say like the light that travels through the top of the slit, the narrow opening, travels a different distance than the light that travels through the bottom of the slit. And since there's a difference in distance, that's going to lead to interference. So I'm just going to throw out there that this is weird. You might be uncomfortable as I work through this little proof. Just roll with it. The examples, I always think, the examples help clarify it. So I'm going to talk you through this. And as always, email me if anything's bugging you. I'll see if I can figure out another way to explain it. We're going to come up with an equation for this, so we need to set up our letters. The good news is our letters are basically the same. Distance to the screen is going to be L. This over here, so my drawing didn't turn out too good. This over here is the screen. So y is going to be the distance from the reference line to the point we're curious about, whether that point is a bright spot or dark spot. That's the same as we called y before. The position can also be measured in terms of the angle in the reference line. That I've just shown there is a right angle triangle. Relative to angle x, the opposite is the y, the adjacent is L, so that's a tan relationship. So just like we did in the double slit proof, we'll use this later. Tan of the angle is y over L. What's new is we don't have two slits, we just have one single slit. That's the opening over here. The width of that opening, I'm going to call that letter W. So W for the width of the opening kind of replaces what we used to have was D for the distance between the two slits. Those are the letters we're going to use. All right, here comes our little derivation. Let's consider out of all the light that goes through that single slit, it's going to go in all sorts of directions, but of all the light that goes through, some is going to hit the screen right at the reference point. So if we consider the light that hits right at the reference point, is that going to be a bright spot or a dark spot? Logic is light from the top of the slit follows this red line, kind of angling downward. Light from the bottom slit follows this line, kind of angling upward. It's so symmetrical that the light from the top coming down and the light from the bottom going up, they travel the exact same distance. Interference was all about that extra distance. In this question, they travel the same distance, so there is no extra distance. However far the light from the top goes, the bottom one goes the exact same distance. So if the top one hits as a crest, then the bottom one's going to hit as a crest. If the top one hits as a trough, the bottom one's going to hit as a trough. Whatever the top one does, the bottom one, since it's going the same distance, is exactly in phase. In phase means it's going to be a bright spot. So if we consider the point right on the reference line, which is an angle of 0, or we could say a y of 0, we haven't moved any centimeters away from the reference line. Just like the double slit, that point is a bright spot. That discussion wasn't wrong, but the scale was way, 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 way off. So I'm not going to change the outcome, but the scale of this is way, way off. If I were to draw it better, remember the W, the width of the opening is going to have to be crazy, crazy small to get this effect. Like if you shine light through something really wide, like a doorway, you don't get an interference pattern. But if you shine light through something crazy, crazy narrow, then we're going to see this weird single slit interference pattern. The W has to be crazy small, especially when we compare it to the L. The L's got to be like millions of times longer than the wavelength. So basically, that drawing that I showed here, that's not wrong, but the scale's way out of whack. Kind of like what we did in the double slit, we had to kind of zoom in to see it better. If we zoom in and see it better, this is really what it should look like. If we focus on the light traveling through the single slit, the L has got to be so huge that that top bundle of light that I said was coming downhill a little bit actually isn't really coming downhill. And the bottom bundle of light isn't really going uphill. The opening is so small, basically what I'm saying on the screen, that would be like literally kilometers to the right. The spot on the screen is basically as big as the opening itself. So instead of thinking of it as a little dot, the dot really takes up some space. So the position on the screen is about as big as a single slit itself. Or another way to think about it, kind of like what we did with double slits, they're not quite parallel, but they're so close to parallel that we can approximate it and presume that these light rays, the one coming from the very top and the one coming from the very bottom, they are parallel, even though they're not perfectly parallel. When we zoom in this crazy much, the second thing that's going to happen, just like it did with the double slit proof, is tan x is approximately the same as sine x. So we know we'll take advantage of this just like we did with the double slits. So if we look at it with this better view, we still get the same outcome. The light that traveled through the top of the slit travels the exact same distance as the light that travels through the bottom of the slit. Since they're the same distance, they're in phase. Since they're in phase, constructive interference. But now let's introduce a little bit of difference in distance. Let's consider a point that's a little bit below the reference line. And when we zoom in, the light traveling through the single slit kind of follows this path that I'm showing in the second picture. The top line travels farther, that one travels farther than that one. If we chop it into a triangle, shoot a line across here, the top one travels this much farther. What I'm proposing is, let's say that that extra distance, the farther that the top one travels, is one full wavelength farther than what the bottom one travels. And if we say that that top one travels one full wavelength farther, so I've kind of cleaned up my triangle, the right angle fits in up here. If I were to chop off this side of the triangle, the same angle x fits in down here. I didn't do a good job of showing you that in the double slit, and I'm not really doing a good job in the single slit either. But whatever the angle to the point is, the same angle shows up inside our triangle. If we do a little bit of trigonometry on that, compared to the angle x, I know the opposite is lambda, and it's opposite the right angle, so the w is the hypotenuse. So from trig on this little triangle, it's a sine relationship. I know the opposite and the hypotenuse. So you can say that the sine of that angle is lambda over w, or if we flip things around, w sine the angle is equal to lambda. So that's our math. Now here's the logic. If the top line travels one full wavelength longer, if the top line travels one full wavelength farther than the bottom line, that means that that middle line, on purpose I'd added a middle line, that this middle distance, that middle one, is only half a wavelength longer than the bottom line. So if the bottom line, it travels the shortest, the middle line travels a little bit farther, the top line travels even farther again. If I'm making the decision, if I'm setting this point such that the top line travels a full wavelength farther, that means the middle one, since it's in the middle, travels half a wavelength farther than the bottom one. That means that, let's say the top one arrived as a crest of a wave, that means that this middle one, since it's half a wavelength different, is going to arrive as a trough. So these two, here, let me get rid of that. Let's think about it another way. If the bottom one arrives as a crest, if the bottom one hits the screen as a crest, the next one is going to be completely out of phase. It's going to arrive as a trough. The crest and the trough are going to cancel out. So this bundle of light right here, this bottom red line, is going to be out of phase with the middle red line. Since they're half a wavelength different, they're out of phase. Out of phase means that they cancel. And now I can go through and do, sometimes I call this like evil twins. If they're for any bundle of light down here, so say this light ray right there, that's partway there, a little bit above that bottom line, there's going to be a light ray a little above the middle line that's half a wavelength longer. So if this bottom, this one I showed down here, if it arrives as a crest, this one's going to arrive as a trough, or vice versa. If this one came as a trough, this one's going to arrive as a crest. Basically, for any light ray that I pick anywhere in this bottom chunk, any light ray I pick down here, there's going to be an evil twin. There's going to be a light ray up here that traveled exactly half a wavelength longer. Since I compare them off, like this one cancels that one, this one cancels that one, I could do that all day long. For every bundle in this, every light ray in the bottom bundle, there's a light ray in the top bundle that's out of phase. Since there's two bundles and they just keep pairing up and canceling off, we're going to get that they completely cancel each other out. And, sorry, bad page break. That half a wavelength completely cancels each other out. For every in the top half, there's one in the bottom half. Since there's a complete canceling, this is going to be a dark spot. Every light ray in the top chunk is canceled by a light ray in the bottom chunk. So it was a bright spot when we're at our angle of 0. It is a dark spot when our angle matches W sine x equals lambda. Because of this even number of bundles and this evil twin pairing off. Let's look at another point. Let's consider a point on the screen that's a little bit farther away. So my angle x is a little bit steeper, and I'm picking a point such that the one that travels the farthest travels 1.5 wavelengths farther than the one that travels the shortest. So this one here, that extra distance from here to here is 1.5 wavelengths. We'll do a similar thing when I chop it into a right angle triangle. If I close this side, that side is W. There's a right angle up here. The same angle X fits into our diagram down here. We get, sorry, that's a little bit messy. We get the same sine relationship. Sine of X, it goes the opposite over the hypotenuse. Just this time the opposite is 1.5 wavelengths. Over the W for the hypotenuse, if I flip-flop things around, W sine X equals 1.5 lambdas. Interference is all about half wavelengths, so I'm always going to divide on the halves. That's why in the last one I divided into 2 bundles. In this particular situation, since it's 3 halves lambda, or 1.5, when I divide on the half, I'm going to divide it into 3. So if the top line is 1.5 wavelengths longer, then partway down, a third of the way down, there's going to be this light is going to be 1 lambda, traveling 1 lambda farther, and then this one's going to be traveling half a lambda farther. So this line here, going to kind of mess up my diagram. This is the shortest down here. This one travels half a wavelength farther. This one travels 1 full wavelength farther. It's a little bit weird, but if you're kind of buying into the logic of this last one, the bottom one traveled the shortest, this one traveled half a wavelength, this one traveled the full wavelength. The logic was that this bottom bundle canceled out with the next bundle. That's kind of what I got going on in this one. This bottom third is going to cancel out with the middle third. For every light ray in the bottom bundle down here, there's one in the middle bundle that's half a wavelength longer. So kind of our evil twin thing. This light ray down here is going to get canceled by that light ray down there. We could do that game all day long. For every bundle of light in the bottom third, there's one in the middle third that cancels it out. So that one cancels with that one. Over and over again, we get this canceling of light rays canceling with light rays. Basically, the bottom third and the middle third cancel each other out. But that means there's nothing left to cancel out the third one. When we divide it into the 1.5 lambda, that's a 3 over 2. Since 3 is an odd number, we don't get a perfect canceling out. There's a little bit left over. Since there's a little bit left over, this is going to be a bright spot. But some of the light did cancel, so it is a bright spot, but it's not as bright as the previous bright spot. I kind of think of this like the older sibling. The younger sibling's not as bright as the older sibling. I can say that because I got 2 older brothers and they were really smart and I was the dim one. So I'm dimmer compared to the previous ones. We're going to keep going with the proof. When the extra distance was a full wavelength longer, we got a dark spot. 2 was an 2 is an even number and there's complete canceling. When the extra distance was 1.5 lambdas, or 3 over 2, 3 is an odd number, so there wasn't complete canceling, so it's a bright spot. It's just not as bright as it was before. If we keep going, I didn't draw the picture for it, but if we kept going and we considered the next point where the top ray traveled a full 2 wavelengths farther, when we divide the trig is going to work out to that. When we group on the 1/2 lambda, interference is always about half lambdas. We got the shortest one, then we got a half a lambda, then we got a full lambda, then we got 3/2 lambda, then the longest one would be the 4/2 or the 2 lambda. When we group on half lambda, we get 4 groups. Since there's 4 groups, 4 is an even number. For every one in the bottom bundle, there's going to be one in the second bundle that cancels it out, so the sort of bottom 2 bundles will cancel. So we're going to have something like this. If this is our W and our reference line, we're going to have like boom, boom, and then 2 more lines in the middle. So we got, oops, I didn't draw that right. Sorry, this is why I type things instead of trying to work off the cuff. If this is our opening, I have to add 3 lines in the middle. So the bottom 2 cancel each other out, and then the next 2 cancel each other out. Since it's an even number, I've divided it into 1, 2, 3, 4 bundles, 4 groups. It's a complete canceling out. The bottom one cancels the second one, then the third one cancels the fourth one. Complete canceling, we get it to be a dark spot. I didn't draw it, but if we went one more, if we picked a point such that the longest distance was 5/2 lambda, our trig gives W sine x equals 5/2 lambda. When we group on the 1/2 lambdas, we get 5 groups. 5 is an odd number, so the bottom 2 will cancel out, the next 2 will cancel out, but there's that 5th bundle that doesn't get canceled out. Since it doesn't get canceled out, it's a bright spot, but since more of the light did cancel, it's not as bright as the one before. Okay, going to summarize this. At the very, very beginning, we did a small angle approximation. We know that tan x was y/L, and because of the small angle, we can say that sine x is basically the same as tan x, so sine x is going to be y/L. So if you look at our pattern of where the dark spots were, they were at 1 lambda, we drew that one. They were at 2 lambda, I didn't draw that one. Definitely didn't draw 3 lambda. But the dark spots occur when we group on a half, we get an even number of groupings. So that means they occur at 1 lambda, 2 lambda, 3 lambda. The trig was W sine x was equal to those numbers. And from our small angle approximation, sine x is the same as y/L, so W y/L is equal to those numbers. So we can say that our dark spots occur at W sine x equals W y/L, and that's equal to n lambda. So it's kind of like we saw with the double slit. We're going to have 2 versions of the equation. If we're working with angles, we would say W sine x equals n lambda. That's going to describe a dark spot. Or if we're working with positions instead of angles, we would say WY/L equals n lambda. That also describes the dark spots. The bright spots are a little bit weird. They happened at the 0 point, and then they happened at the halves, 1.5, 2.5, 3.5. So we're going to get 2 equations again. For the bright spots, we're going to say W sine x is when we're off by a half. Or if we're not measuring angles, we're measuring positions, WY/L, we're going to be off plus a half. Oops, ran out of room. Sorry, that's really messy. Let's try that again. The WY/L, if we're measuring positions, is off plus a half. And also for the bright spots, that 0 degrees was also a bright spot. What this means, so almost done, what this means is, notice that we've got 1 lambda, then 2 lambda, then 3 lambda for our dark spots. And for our bright spots, we've got 0, 1.5, 2.5, 3.5. What didn't show up was the extra distance being half a wavelength. What that means buried in the math is when we look at a single slit pattern, it's different than the double slit. Double slit, evenly spaced smudges of light. The grading pattern, also evenly spaced, but I would call those narrow bands or stripes of light. For the double slit, so in this picture here, The red is where the light is hitting, the black is where there's no light. Notice that that middle bright spot is wider than the others. That's where that 1/2 that kind of got skipped is. Our first dark spot doesn't happen until the extra distance was a full wavelength, and then they alternate, changing by half a wavelength. So I know it's weird and I'm probably not describing it very well, but in a single slit pattern, the central bright spot is brighter because all of the light, none of the light got canceled, and it's a little bit wider. Basically, it's twice as wide as the rest, so it's no longer evenly spaced. And the outer bright spots, this particular one that I found doesn't show very well, but those outer bright spots get dimmer and dimmer and dimmer. You can kind of see it with this sideways graph. So the single slit pattern, bottom line is it's just different. The proofs are a little bit different. We end up with a central bright spot that's really bright and wider, and then evenly spaced after that, and getting significantly dimmer as we go. I think that's all the talking I want to do about single slits. Notice it's basically the same equation. We've got the sine x and the w instead of d, but we've got the w sine x and wy over l, but it's kind of flipped. The dark spots now line up with the n lambda, and the bright spots now line up with the n plus a half lambda. That's where I'll pause. I suspect this has not gone 100% smooth, but I honestly think if you take some time, work through these 3 examples, listen to me talking through the examples, that'll help make sense of it. That same worksheet, we can now finish it, and there's one check-in related to this stuff as well. As always, email if you have any questions.